data structures. Much simpler, I know. So like obviously, like when you're doing your DP, right? Like you store it in an array, right? That's usually what you do in your DPs. You memo with an array, and you use the array to look up data and do your transition, right? But like arrays are weak and flimsy, right? Why can't we do it with a better data structure than an array? Like how do you consider what?
Point update, point query, segment tree.
So true. That's pretty good. That means our updates are logarithmic in time instead of O1. Okay, so the main general idea that you tend to come up with like data structure DP problems is you have like when you have some like sort of like recurrence on some range. So like let's say you have your DP, you have DP of I is equal to some function that acts on DP of J all the way to DP of K, where J is less than K is less than I. And so obviously, like looping through this, like this range could hypothetically be up to whatever the size of this state is. There's no real bound on it. So instead of looping through all the like previous DP values and combining them with the function, what we could do instead is we could just calculate this function using a range query instead. And so we can use some sort of range query and data structure to do that instead. So we're going to go over a starter problem. Thomas, you don't have to listen to this one because you made this problem. Oh yeah. So you have a dice, right? And this looks like a 6-sided dice, but I swear it has n sides. Trust me, up to 10 to the 6. And you are also given Q queries, which is up to 10 to the 4. And you basically, each of these queries gives you some number k sub I, which is also up to 10 to the 6. And so what you're asked is, you're going to keep rolling this dice. You want to find out what is the probability that there is a point, like at some point during the rolling, that all of your dice rolls sum up to exactly k sub I, and you answer that for each query. Anyone, ideas, any observations?
You keep rolling while the sum is less than k sub I. Once it goes over, you lose.
Okay, yeah.
Slam the n times q. Maybe with like a fixed.
What's the n? I feel like there's a part here you're failing to consider. Yeah.
Slam the n times max k times or plus q.
True. Yeah, so I mean, yeah, that's like what you're going to start with, right? Is like you're going to naturally like keep your DP table of like what's the probability of getting each of these sums, and then like for each possible dice roll you can make, you can like go back in your DP table and sort of like add those all together and like divide that by the probability of rolling a specific number, right? Because like each of the previous ones, like, yeah. So that's like slow though, like n is 10 to the 6, k sub I is 10 to the 6. Does anyone have any ideas how we could speed that up?
A data structure.
That's true. What data structure?
Segment tree.
So true. We can definitely do a segment tree, right? Because like we're getting a range sum here. So obviously if we're using a segment tree, then we can just like get a range sum. So like what we do is like we just store our DP values in the segment tree. And then instead of having to go back and like let's say our dice has 3 sides, instead of having to go back and query, like go back and loop through each of these individually, we could just do a range sum on our segment tree with these guys and then update it, and it's like pretty simple. So that's like O of n log n plus q log n or something, right? Okay, cool, now do it in linear.
Well, q isn't real.
Okay, yeah, true.
you don't need to update it, so use a prefix sum instead.
True, yeah. So like, you can instead, the actual like canonical solution to this problem is a prefix sum, which like, you can just like store in your DP state instead of it storing, oh my god, it keeps falling over. Instead of storing your value just for that specific state, you can instead store the value that's the sum of all the previous states, right? And so you can simply get the range sum in O of 1 that way by just doing a single prefix sum query, and because you're not like actually updating anything like in the middle while you're doing that, it's like, fine, what?
Is prefix sum a data structure?
It's close enough as far as I'm concerned.
Definitely.
I would consider it a data structure.
It's a structure of data.
It kind of is weird to think about it as a data structure, but I think it's good as like a starting example for like the rest of the stuff I'm going to cover, right? So yeah, that's prefix sum DP. But like obviously, range querying data structures are not the only type of data structure. There are other ways in which we can use data structures to make our DPs a lot better that aren't with range queries, because we, like for example, what if we have some DP where instead of like, where the state space is like in theory very large, but we actually only are visiting a small series of those states. So, an example problem here, we have another dice. Unfortunately, the problem isn't about the dice this time, it's more like, and this one is like exactly 6 sides. And you are also given a line of n dominoes, where n is up to 3 times 10 to the 5th. So like each of these dominoes are going to be in a line. Let's say we have 8 for now. And then like you're going to repeatedly roll this dice. And each time you roll this dice, what you do is you take the domino at that position. So let's say it rolled a 2, which is the 2's on top. So we're going to remove domino number 2, and then we're also going to remove every single domino that is 6 positions after, like multiples of 6 positions after that one. So 8 also gets removed. And then after each removal, we're going to like reorder them. So you're going to repeatedly do this process. Eventually, there's going to be 1 domino left over. And what you want to find is for each starting position of the dominoes, what is the probability that it will be like the last one remaining?
So this n is like the number of dominoes that it stops.
Yeah. Anything?
You can like represent not like the number I don't know the exact construction, but like you might be able to represent instead of the dominoes you have left the like modulo relations of like when you marked guys.
You can do this problem with just storing how many dominoes you have left, actually.
Does that? Because that like it decreases by like it like decreases by a log step, but
Yeah, so
does that just work? I guess it might.
first, yeah, we should first figure out like how many rounds is this gonna last. So like every time like we do a round, about like on average it's gonna be like n is gonna be multiplied by 5 over 6, or I guess divided by 6 over 5. And so to get the number of rounds it's gonna last at the maximum n, what we can do is we can do log base 6 over 5 of 3 times 10 to the 5th. And so this is actually going to be only around 70-ish rounds. So this is not very much, but it still does look sketchy, right? So the other thing you can realize is like, so let's say right now our DP is going to be like DP of ij. It's like i's position of current domino, and j is like number left. What we can realize is this left number, like it doesn't like the state space for this doesn't expand, like, it expands very slowly. Because like every time you do a removal, like the actual amount of dominoes is only ever possibly going to change by 1. Because either you remove, because like, if you could like remove 2 more dominoes in some case than another case, that's like impossible, because like you have to fill up like 1 modulo bracket before you fill up the next, so they're only going to differ by 1.
So wait, your state space for your DP is the position, and then what is left the number of dominoes left?
Yeah.
Okay.
So yeah, obviously this is like n squared, right? But so yeah, this expands very slowly because of like it can only ever change by 1, and also it's also very likely for there to be like collisions. Like you could remove 1 from each. Like you could have k and then k plus 1, and then these could also possibly end up at like very similar values down the line as well. So the actual number of states we would visit in this DP is very low. Oh, yeah. So the actual number of states in this DP is very low, and we can exploit this using everyone's favorite data structure, a map. Yeah. So we can store a map of like our state to our resulting value. And because like the actual state space isn't going to be very big, like this actually runs in time. Like the time limit is like 5 seconds, and you can get solutions to run in like a second or 2. Yeah.
So you're storing the leftmost domino in the number that are left? Or what is the position?
Well, we have to solve it for all initial positions. So we're keeping track of what position it's currently at, so we can know like when we're doing a removal, like what happens.
Wait, what do you mean by all initial positions? Like, are you
Well,
saying?
because we have to solve for every single initial domino. What is the probability that's the last one surviving?
So you're just like solving the problem independently for each starting domino?
Oh,
Yeah.
so you're keeping track of just what the chance of it getting removed in general,
Mhm.
and the number that are left. Okay.
Yeah, and so also important speed up to keep in mind for this problem. Like I initially thought you should do a map of pair to int or whatever like type you're using for your result. You should actually do a map of int to vector int. This is faster because you store your second state in a vector rather than a map, so you have to do less map transitions. I was like, why is my code so slow? That's why.
Wait, so you're saying the vector int,
Like, so this is like, int is just like for your first state, and then the vector int stores it for your second state.
What are
but
the
that would
states?
imply that the vector int, like, it's big, right? So that would, you would need to like know that only the first part of the state has a limited number of values for that to work in
So
memory, right?
is int,
I think if you do like left as this state,
Okay.
it's fine because,
because I is not actually like sparse, right?
yeah.
Makes sense.
I unfortunately do not have like a very exact like explanation of the solution. Does anyone have any questions about this?
Is there no part of your state that's like number of rounds, or are you just having that implicitly based off the number of guys?
The number of rounds doesn't matter. You keep rolling until all the guys get removed. And like, if you're wondering about like, oh, what if you roll a number and you have like less than 6, but you roll a 6, you just ignore it and keep going.
Okay.
You're just trying to find what's the probability that this guy's the last one.
So you have to do like a little bit of like cycle elimination at the end?
No, not really, because you can just like, because like the cycle is a self loop, so like you can just like ignore it. Like the probabilities stay the same because you're just re-rolling until you hit one of the like actual ones. Okay. So yeah, that's one thing you can do with maps, but there's also like, maps can also be even more useful for DPs. Not only can you, like obviously it helped a lot with like space saving in this instance, but it also means like, they can also help you a lot with sort of skipping transitions. And Here's another HSVT problem, everyone's favorite. So, in this problem, you have a number line, I believe it is like 10 to the 5 log. Yeah, and yeah, you have some starting position S, which is bounded by 10 to the 5, and you also have some number N, which is bounded by 10 to the 5, which represents the number of meteors that are about to hit this number line. Before each meteor hits, you are given you are allowed to move around this number line as much as you want before the next meteor hits. You're not constrained by time or anything. However, you do want to minimize the total distance you travel. So when each meteor hits, you're gonna, it's going to have 2 endpoints at different parts of the number line. And if you are in this area, then you lose. And you don't want to do that. So you have to find the minimum distance you have to travel around the number line in order to not lose. Yeah.
So you're saying that the meteors, they have a width, right?
I guess you could say that, but it's defined by endpoints, not a radius or anything.
Yeah, I just meant it's not unit.
Yeah, they're not unit, no.
And you move between each meteor, or
You can move as much as you want before each meteor hits. You just want to minimize the total distance you move. It's not there's no time constraint or anything.
You're just given that they fall in succession.
Yeah.
And I don't think you're guaranteed that there won't be a media that covers the entire range.
I think there is technically not a bound on the range. It's just these are the bounds of the all the coordinates.
Oh, okay.
Also, if you move to an endpoint, you can be in the endpoint and still be fine.
Oh, sure. Yeah.
Any observations?
you have two options, you move left or right, and that's basically the states. For each index, if you're left or right.
I mean, that's true, but you can also not move. Because you're not always going, let's say, okay, cool, my starting position is right here. Okay, hi, I'm a little guy, I'm right here, right? Cool, meteor hits over here. Do you move? Is there any point in moving? There's not really a point in moving, because all moving would do would mean it would help you avoid a future meteor, which you can just do that when the time comes, so you don't actually have to move at that time. So anytime we're not in range of a meteor, we actually shouldn't ever move. So that's one greedy observation. But you are right that when you are getting hit by a meteor, you obviously just want to move strictly to the left or right endpoints. Because again, moving further is only going to help you avoid a future meteor. Yeah?
I don't know if this is helpful, but there's no difference between moving now versus moving right before one of the future meteors.
Yeah, that's basically what I'm saying. Yeah.
Well, you were saying you just want to go directly to an endpoint, right?
Yeah.
Yeah, I was saying if there are 5 meteors before you have to move, there's no difference between moving right away or moving right before the 5th one.
Well, for each of the meteors that
Well,
don't intersect you won't move.
Yeah.
No, because you might have to avoid some meteors on the way to avoiding the 5th one.
No, I'm saying if none of them hit you, but
Yeah.
the 5th one does. I'm just saying you can kind of move state around it.
Yeah. Yeah, I agree with that. So the question is, how can we exploit those observations in a DP? Because obviously if you store your DP is position and meteor. Oops, we did it and squared again. So one thing we can do, okay, I'm gonna make a series of adjustments that don't seem like they're going to do anything, but will eventually result in something. So first what we're gonna do is, instead of having an index for the meteor, we're just gonna remove that and make it a transition instead. So we're just gonna have our vector for our DP, and it's just gonna store for each position what its current DP value is. again, this is still n squared because we're gonna have to loop over all the guys to update them.
The DP value being like the minimum time it takes to be at this point while still having avoided the prefix of meteors.
Yeah. Right, so. Yeah, so obviously this is still gonna be n squared, we have to loop through all the guys and like update them each meteor. But actually, no we don't, because again, if you're not in range of the meteor, you don't have to move, which we've already established. So like if you don't have to move, we're like fine. So like we can just like update the positions in range of the meteor. But again, this can still be n squared because it can be as big as the whole number line. So what do we do now? Okay, well, instead of using a vector, let's use a map. The map is back. And why would we want to use a map? Well, let's think about it this way. So each meteor is defined by two values, an L and an R, right? And then we have our starting position. So in total, we're going to have like 2n plus 1 possible positions. And so if we can find a way to only process like these positions like a constant number of times, then we're doing pretty good. Like that's like linear runtime. So what we can do is when we only add a position to the map. Oops. So let's say we're on meteor I and we're getting hit by a meteor. We only have to add that like position to the map when we first get to that point. Because so we're only considering now like points that are either the start or end points of meteors. So this adding to the map is just going to be one operation for insertion. Well, technically it's log time, but it is one operation, I guess. And then the other thing is, well, we can use lower bound on the map to find the first position that's within range of any meteor, and then we can go up through all of those positions to find the ones that we actually need to move. And so that means each position is having one operation for its removal, basically, or a constant. At least it's a constant number. And so what we're going to end up doing is each state in the map is only going to be processed twice, and so therefore the runtime of this is actually going to be n log n.
Well, when you say state, do you mean position?
Yeah.
Well, like, that's not strictly true. Like, you're saying like each state at a given point in time, because you could like,
Okay.
you
Like,
could
I
get
know
back
you
to a
can-
spot. You're saying it amortizes. Like, when you say position, right, like you can get back to a position.
Yeah, you can
Like,
get back to a position.
That new guy is
But
a new
obviously,
guy.
like we can only if we can still just treat that as like a new distinct position, and like we said, it's bound. The number of his positions is bounded by 2 times n plus 1, because again, just the starting position and then the left and right endpoints for each meteor.
So what is the final DP structure? It's just the one map, or there's a map of something else to it?
It's just the one map, and then you do lower bound to like get the ranges of guys that you need to like update, and then you insert the left and right.
It's like sort of iterative, but with
Yeah.
And you gotta like delete the guys.
Yeah. Any further questions? All right. It's segment tree time, I guess. Clapping for the segment tree, but not the prefix. I'm unbelievable. So, yeah, segment trees are obviously like very useful for these types of problems because all of like the previous things that we've mentioned that you can do with data structures, segment trees are at least like pretty decent at all of them. Like you can, like it's like obviously really good at range queries, and you can do space saving with implicit segment trees, and then also you can, yeah, that sort of like sweeping transition thing on segment trees as well. And obviously with segment trees, like the most common sort of DP problem that ends up getting used with them is LIS. I'm not gonna go into like a super in-depth explanation on how you do LIS with segment tree, because I'm kind of assuming most people kind of already know it, but like the gist is like for each like value, it stores like what is the length of the longest increasing subsequence ending at this value, and then if we're going to add a value like 3, then we can just check like the length, like the longest lengths ending at 2 and 1, and then take that, like take the max of those and then add 1, and then update the state. Yeah?
At that point, is it better to just use a bit?
No, because it requires max.
Yeah, but it's only increasing, so you can use a bit.
You can, but like, be real.
Okay,
That's
well
not
I
what it
can't
is.
code a bit from memory, so at least with segment tree. Yeah. So the reason why I am mentioning this though is there's like a pretty like sizable amount of problems where it is like you can do like where the problem is n log n LIS, but it's like obscured in some way. And I'm going to go over a problem that's similar to something we've had on like a Saturday set, but it's not exactly the same. It's a bit easier, but only barely. So you're given a number n. It's 10 to the 5th. Okay, it's bounded by 10 to the 5th, and then you're given 2 permutations of n numbers. One occurrence of like, so every number from 1 to n occurs once in each permutation, right? So you want to find between these 2 permutations, what is the longest common subsequence? Any ideas?
LCSDP, it's squared, call it a day.
Yeah, no, you can't do it at squared, it's 10 to the 5th. I love 10 to the 10 operations. Yeah?
Can you like apply one permutation to the other and do like LIS?
I mean, that sounds like essentially the gist of the solution. I wouldn't say apply one permutation, but like what you can do is for each, like for it's like some number 3, we can get its indices in like both of the permutations. So let's say this is like 1 and 2. This is a point. I love points, and so what we can realize is if we like chart this on like a coordinate plane, like all these points, it becomes find the sequence of points such that like find the longest sequence of points such that every point is like up and to the right of the previous one that you selected. And so, and yes, you can, yeah?
Sorry, can you repeat what the points are?
The points are you get for each value, get its indices in both permutations. So, yeah, so you get all these points and then you can basically run like some sort of LIS on this to get your answer, because like, obviously, because if you have some number like that occurs after some other number in both permutations, then that means like you can put them after each other, like put one after the other in the LCS. So that's why I'm saying up and to the right. But actually you can just like make this a regular LIS by sorting by one coordinate and then doing LIS on the other coordinate. Any questions about that? Yeah, that's understandable. Okay, but here's another segment tree problem, I guess. I don't really have an introduction for this one, but I guess like thinking about 2D grids though, this is a 2D grid problem. So you have your, again, I guess coordinate plane is fine. It goes from 0, 0 to NN, which is bounded by 10 to the 9, which is a pretty big coordinate plane, I would say. And you want to get from the bottom left corner to the top right corner. And you are only allowed to move up and right, unfortunately, because we have to make this constraint that makes the DP possible, right? So Yeah, but obviously, like, we can calculate this distance very easily. Like, it's 2n, right? So we have to add something that makes the problem actually interesting, which is we have these springboards at certain positions that also launch you to some other ending position, and these also only go up and right, and they do not add to your distance. Like, so basically you want to find like what's the minimum distance you have to walk to get from the bottom left to the top right, and the number of springboards is bounded by 10 to the 5th.
Like Manhattan distance. Manhattan distance. Right.
For the 2n?
Yeah.
Yeah. Everything's Manhattan distance. You can move, like your moves are 1 unit up, 1 unit right. Any observations? Yeah.
When you like process one springboard, you're going to consider like a convex. You can call it convex hold, but like don't think about it as convex hold by of like the springboards that you could jump from, and like that will have some amortizing behavior that you can do that you can exploit with like removing them from the set. I think.
There's a simpler solution.
I don't literally mean anything to do with convex hold trick. I'm saying like when you process a guy, there's going to be like guys that are below it and to the left that you'll remove, and like it's like for loop set basically. I think, yeah. Do you get what I'm saying? Do you?
I kind of get it. I know there is a solution to this problem with that uses like some sort of map, but it's like it was made to be like harder to derive than.
Don't necessarily want to take something on the convex hold though.
Oh.
Like you might want to go past it.
But
Take
that
something
guy.
else.
Yeah.
No, but like the
So-
other, when you go past it, you might be able to jump further.
For each springboard, you can choose either take it or not, and I presume you'd be doing some sort of range queries on previous springboards, or like the ones
Yeah, like-
below and to
It's
the
like,
left.
it's like
Kind of, but the way I thought about this problem was a bit different, which is like let's have instead of like caring about the springboards, let's care about what y value the springboards end at, and so we can have like our dp table store like dp of y is equal to like basically the equivalent to minimizing our walking distance is also maximizing the amount of distance covered by springboards. That is equivalent. So what we want, so let's say dp of y is equal to the maximum amount of distance we can cover, like we can cover with springboards, such that like the last springboard we take ends at position y, like ends at some y value.
Wait, do the springboards have? What do the springboards do? I think I've.
They launch you, that you were given a start point and you're given an end point. The end point is always up and to the right of the start point.
Oh, okay. I think I misinterpreted it.
Oh. So, and then obviously we can, since we're storing one coordinate, we can do a sweep on the other coordinate. So for each springboard, like we can process its start point and then like store that value for like later to update its endpoint, I guess. So like we're gonna have a segment tree. This is gonna be implicit because of 9. So we're gonna have our segment tree. And so, like, let's say we have some, like, let's say we have this set of springboards. Let's say 0, 1, 2, 2, 2, and I guess 0, 3, 2, 2, 3. So the first one we're going to process is, I guess, this one. So our reduction in all of these is going to be 0. And so, like we check, so our y value is 1. So we check like everything less than or equal to 1 to find our maximum reduction. We find that it's 0 because we haven't taken any springboards before this. And so we're going to keep that in mind for this endpoint, that their total amount of reduction is gonna be 0 plus like the Manhattan distance between these two, which is 3.
Can you draw out the case?
Okay. So this is 0, 0. I'm coming up with this case on the fly, so like I don't really have like an example on hand, unfortunately. And then 0, 3 to 2, 3. So, yeah, so we're gonna keep that in mind for when so this is a Manhattan distance of 3. So it's gonna be the max reduction, which is 0. This is a bad case because we're not gonna have, like, the springboards don't overlap anyway, but like, yeah. So then we check this point, check the segment tree, it's 0. So this is 0 plus 2 because the total distance covered by the springboard is 2. And then we process this endpoint afterwards because we're sweeping on X, I believe, and we now update the segment tree with our reduction, which is, we're at a Y value of 2, so we update this to 3, and then for this, we update this to 2. And so like on future, if we had more springboards, then we would use those values in the segment tree instead. And obviously, like, for some, like, if you're some Y coordinate, you're only querying Y coordinates like below you. Are you raising your hand, or are you just?
Yeah. How do you process the queries? Because you cannot process like a springboard that leads you to a point that later you cannot come back to another springboard.
So what I did is like I sorted like all the start points of the springboards by X, and then I put them in a priority queue because the priority queue makes things really easy. Because what you can do is when you process some start point, you can like store the value for its endpoint somewhere and then insert that into the priority queue. And then once you process that endpoint, you use that value that you've stored to update the segment tree.
Like, what order are you doing the updates? What order are you processing the points in?
I believe I did them in like prioritize X coordinate. Like, you process them in order of like X coordinate, and then technically you should do like reverse Y coordinate probably, but I don't think it matters. I'm not sure. I think also if you have an endpoint, like you process all the endpoints before any start points at a given X value. So like their values can be used by those start points. Any other questions? I know I didn't do the best job at explaining this problem, but
My priority queue is clean.
yeah. How much time is left?
About 20 minutes.
Oh, okay, we're fine. I might have to go into problems that I didn't write notes on then. And so yeah, this is the last problem that I had prepared, but I do have some other problems that I had unprepared, but it's like fine. So you might have heard me talk about this problem a bit. I like this problem. So in this problem, you have n days, which is bounded by 2 times 10 to the 5th. And you have, there are m museum visits, museum exhibits, which is also bounded by 2 times 10 to the 5th. And so each of these m exhibits has a certain range of the n days that they're open on. And so, like you'll be given the ranges for each of the m's. And also, you have an array of n numbers. And this represents, like, on day I, like the way the problem is, it calls it like discomfort level. Like when you visit, if you were to visit a museum, like an exhibit on some day, like that is the amount of discomfort you would get. But the thing is though, and this is like the caveat of the problem, if you visit you can visit any number of exhibits on the same day, and you will only incur like the penalty for the day once. So like it's not for each exhibit you visit, it's just a one-time thing, and you can visit as many as you want on that day. Yeah?
So you're saying that the museums, like the days that you can visit them are given by the ranges, right?
Yeah.
And then you can, like, each visit is independent of each other one, is just like, can only be on one of the days of that range.
I mean, technically not, but I don't think like it's always optimal in this problem to only do it on one day. But what I'm saying is like, for some day, let's say like you have like 3 different ranges that cover that day. You can visit all 3 of those on the same day,
Oh, it's
and
just
you
one is
only
covered.
you only incur the penalty
I see.
once. And so what the problem is asking is, what is the minimum total penalty you need to visit every single exhibit? Any observations on this? Yep.
So for each position, you would want to know how many are overlapping it to start with.
What do you mean by overlapping?
Like the number of intervals overlapping that index. For that day, right?
That definitely helps, but the problem is the way the ranges are now, it's not really super clean to do that. Cause like our goal is like, get the range, like get its ranges in a way that you can handle each range like cleanly.
I
Yes.
spent a lot of time on the problem, I couldn't solve it. Like, my base idea was that for each museum, you get like the minimum on that range. You know that the worst that you can do for a museum is the minimum on that range. And basically like, you update that range, like you make like a score for it's like the sum of all the minimums that occur in that range. I don't know if you understand, like, it's kind of weird like that.
I'm not really following there. Yeah.
Would you be able to sort the intervals and then do some sort of like sliding window?
Not how they are arranged right now.
Well, I said sorted.
Again, not how it's set up right now. You can't do, consider the following, you have one, okay, the reason why you can't sort them is, like, I'm gonna show you a case where that is an issue, which is, let's have one range be like this, and let's have another range be like this. You can't do a sliding window on this because this starts and ends the entire time that this range is in there. But there is one observation on this problem that means you can do a sort of sliding window thing, and I think I'm just gonna go over it now, which is, like, this is the only problem, is when you have these sort of nested ranges. But the thing is, if you have to visit a museum on the inner range, then you don't care about the outer range, because the inner range is always like if you visit something here, this requirement is satisfied, you don't need to do anything extra. So now what we can do is get all the ranges that do not have another range nested in them, and now we only care about those ranges. Do I need to go over how to do that, or?
You should.
Okay, yeah, so I guess mini lecture in the lecture, we're gonna solve nested ranges.
Or not I mean like the rest of the problem.
What?
I thought you mean the rest of the problem, not like the nested ranges.
I was specifically talking about this.
Like, do you know how to get the nested ranges? Like,
Yeah.
get the guy, okay, well, like, does everybody know how to do it?
Anyone else want me to cover that, or, okay, sure. So yeah, we have our ranges now, and now, what we can observe is that like, anytime, like, now our ranges are in a way where if we sort them, then we can do we can like do, forgive me for this, ranges of ranges. Like, we can treat like a sequence of ranges by a range, because earlier when we had our nested ranges, we could have like an add and a removal. So if we had like, So we would add 1, 2, 3, 4 here, and then subtract out 3, so now this would be 1, 2, and 4, and that is not a contiguous range. But when we have this sort of setup, now these all become contiguous ranges, because by definition, like the first range's endpoint has to be like at or before the next range's endpoint. Because if it wasn't, then it would imply nesting. So now that we have these ranges, what we can do is for each element of the array, you can like get, okay, let's get a set of ranges here. Let's move this here. Let's say these are our ranges. So for each element of the array, we can get like the range of ranges that it covers. And so now, when we take, what we can do is we can build our segment tree now. Oops, forgot one. And now, like let's say, and now we can sweep through this entire array. And for each of these ranges, oh, I guess I drew too many nodes. We're gonna have like a node in the segment tree for it. And what we're gonna say is, like that is going to be like the minimum penalty required such that you have visited all exhibits and like you have selected a value in like the entire prefix of those ranges. So let's say we're at the state now, like let's say we're at 2, and so we've already solved it for range 1, like it's 1 because it's less than the minimum. So, and then we should have 1 for 0 also. I forgot that this is not a segment tree anymore, but like it's fine. So now, when we process 2, this covers the ranges 1 to 2. So since this solves 1 to 2, we can query everything from 0 to 2 because, yeah. So this, and so we get our min here, which would be 0, and then add 2, so we get 2. And that covers both of the ranges there. And then we can just keep doing this, and eventually whatever ends up in our last spot here, I guess M, that's gonna be what our answer is. Any questions about that, or like?
So what's the range you're querying for every point that you process?
The range I'm querying is basically like the range of the ranges it covers minus 1, like
Ranges
on the
in
beginning.
sort of order by left to right, right?
Yeah.
Not their original ranges.
Yeah, we have to query minus 1 because if we have it completed to 1 before the ranges it covers, then if we complete all those ranges, like that'll continue the prefix. Any other questions about this? Okay, I guess I have to go into problems that I did not prepare unless we're like out of time. We still have time though,
It's
right?
11:55, so it's up to you.
It's up to you. You can have 0 minutes or 5 minutes or 10 minutes.
I guess let's go over one more problem.
So,
Yeah, I don't have this one noted down, so I might get the bounds wrong. This is an OCPC problem.
yeah.
So you have an array of n numbers, where n is up to 2 times 10 to the 5th. And then also each of the values in the array are bounded by 1000. And what you want to do is you're also given a number k, which is bounded by n. So what you're going to do is you're going to split the array into like k contiguous disjoint subarrays, such that like each element is in exactly one subarray. And what you want to find is, you want to find like, what is the, I have to, I believe it's the maximum minimum average on that you can achieve on any of those K segments. Yeah?
Did you say that each number can only show up in one once, or were you just talking about like an index?
I meant index. Each index can only be
Okay.
is in exactly one
So
subarray.
you're splitting it into K ranges such that for each range has some average
You want to maximize the minimum of those averages.
to maximize the minimum.
Yep.
Would you be able to do some sort of binary search on answer for this?
Yes, that is part of it. You binary search on what the average is. I'll tell you that.
Okay.
And the reason also why this bound is like this, where it's like 1,000, like it looks important. This is actually just to help you with precision because the epsilon is absolute 10 to the negative 4. So you can multiply everything and do everything with integers. So I think that's the only reason why the bound is like that. So yeah, part of this is going to be binary search on average.
What was it? You want to maximize the minimum average?
Yeah. I'm guessing no other observations here. Well, okay, so here's the thing, this is actually secretly an LIS problem. So what you do is you get your array, right? And so now you subtract out the average that you're binary searching on from every single element to get like its deviation from the average. Then prefix sum this array. And then you do LIS on it with some like weird constraints. And the reason why this works is because like for some like range, right, you can only take it in the binary search if it is above the average, which means if you're summing up every element's deviation from like the intended average, that has to be positive. And since you have to cover the entire array, you also have to take like continuous sequences. So so like each of the prefix sum values has to be like non-decreasing.
That's
so true.
And you need to take the last value too, right?
Yeah, you also need to take the first and the last value,
This is a problem.
which makes things a bit awkward to implement, but
It's too clean.
Why the first value?
what?
0.
Well, because like, then you could start with like a negative number and get something longer.
Oh, yeah.
And like, 'cause you have to cover
So
the
first
entire
value,
array,
you
so
have
have
like
the first
the
and
prefix
the
sum
last.
of like n plus 1, and you got like a 0.
It says 1, so it makes
How do you ensure, do you need to ensure you get exactly k, or if you solve it from, if your LIS is more than k, is that?
The idea is like,
It does the better.
if you get more than k for some like average, then
Oh,
you
you
can
can
like
always-
combine them,
yeah.
and like all of the averages will still end up more
The
than that.
LIS has to be like bigger than K.
So
Or
the
you-
yeah,
Greater than or equal to.
the LIS with the first and last element has to be at least k long.
Yeah. Technically not a data structure problem because the better implementation for this is using LIS pack because it's faster, but like, because this is log squared because you have to do a binary search and then LIS, but
Anything in hackback is a data structure.
fair enough. I guess that's basically it for the lecture though.